Hey, hi, welcome. We are going to talk about lesson 4.1 today, identifying linear functions. We've been looking at different types of functions, and we know that we can see a function as a table, a graph, a mapping diagram. We know that all these represent functions or relations. What we want to talk about today are linear functions. And we know if we look at the word linear, we see line as its root term. Line indicating the shortest distance between 2 points. So you can see from that definition that a line is not curved ever. Being the shortest distance, it has to be straight, and that's how we define line. Look at all these beautiful colors. Let's pick that one. Okay, so moving ahead here. In chapter 4, lesson 1, we look at different examples of what they want us to see. We have one example looking like this. We understand that is not the shortest distance between any point, any set of points. If we look at this, we can remember, because these are coming up quickly, this is called a quadratic equation. Quadratic, because there will be some relationship between y and, that's not what I wanted, and x to the second power. So anytime we see x to the second power, we know that we're looking at a parabolic function, also known as quadratic. The one thing we talked about early on in the year, we talked about the vertical line test, and we can see on this green grid down below, we can see that if we had a perfectly horizontal line in the coordinate plane, we have a function because of the simple test that we used, which was called the vertical line test. When we started talking about functions, we started using the lingo vertical line test. Now if we take a vertical line, let's see if I can do this. Vertical line, whoops, not so vertical anymore. And if I take that and run it over the purple line, I can see that I only touch that line in one point. This to me says that we've passed the vertical line test, and therefore, 3 dots, therefore, we have a function. That's the vertical line test. So let's take a look at the next scenario. Coordinate plane, and this time, we have a vertical line. Let's say it passes through x equals 3. Well, this time, taking my vertical line, let's do one of these jobby-doos. There's close to vertical. If I take that vertical line and I pass it over that vertical line, I see that I touch that line x equals 3 in infinite spots. And what we do with this is we conclude, therefore, not a function, because it failed our vertical line test. Fail. That's not a fun word, is it? The next way that we can assess whether we have a linear function is to look at a table of values. What I'm looking for in a table of values are equal changes in x compared with equal changes in y. So if I look at this table of values, I can see the following. The y values are changing by 2 each time, as the x values are changing by 1. And we remember from middle school. We don't want to remember a lot from middle school, but one thing that we do want to take out of it are all those math tools that Mrs. McKinstry or Mr. Calhoun taught us, and that was any function in this form. This m value indicates our slope, or the change in the y values, which we just showed right there, compared to the change in the x values. Remember the Greek symbol delta indicates change. This one actually looks like a poop emoji, but sorry about that. It means delta. So we're looking at the change in y being 2 in this case, and the change in x being 1. And so that would indicate the slope of our line. So we could write y equals 2x. And if we thought about it hard enough, where does a line pass through the y-axis, which is what that b value indicates? It says, I am the y-intercept. So when we're making these functions from a table of values, if x were 0, y equals, our slope is 2, 2 times 0, we let x equal 0, and what do we have? We get y equals b. Y equals b, that means the y value is b. We look in our table where x is 0, and we see that our y value, or our y-intercept, 0, 8. 8 is where the line will pass through the y-axis. And we could start to graph these points. 1, 10, 2, 12, and we can see this line increasing with a positive correlation or a positive slope. And that brings everything in algebra back together again. It's just as simple as that, folks. So on your sheet where you're taking your notes, here's what I'd like you to do. Define slope, the slope of a line. You can talk about it in terms of a table or a graph or the equation, but I want you to define slope on your note worksheet. And when you get to this point, I want you to bring it to me and show me that definition. I would also like you to consider the check it out problems, 1A, B, and C. Check it out, 1A, B, and C, and 2, just 2. Check it out, 1A, B, C, and check it out problem number 2. And we're going to come right back here. Turn this off, please, and we'll come back and talk about those problems. And we're back. I'm looking at check it out problems 1A, B, and C. And you notice that before when I talked about these problems, we could use the vertical line test to tell whether a graph represents a function, and then we want to talk about whether it's linear or not. So in the case where it is a function, we're just going to take this fancy vertical line here that moves across the page for us, and we can see as we move that across, we do have a function, yes. And is it linear? Well, if I pick any 2 points on that function, I can see that they have definitely covered the shortest distance between any 2 points. Same thing's going to happen over here with 1B. I take my vertical line. You could use a card or your pencil, and I can see, obviously, this guy is also a function. So we're going to say yes, yes to function, and is it linear? Again, choosing any 2 points, we can see that we've traveled the shortest distance between those 2 points, and so yes and yes, function and linear on both of those. Well, let's take a look at 1C. We're going to move our vertical line. We already know what our result is. We're going to take our vertical line, and we can see, other than at that point right there where it touches in one spot, we can see that this vertical line touches in 2 spots from x equals 0 to infinity. So we have this for our answer. No, it's not a function, and therefore it can't be linear. So we're just going to take a quick look at check it out problem number 2, and it asks us to tell whether the set of ordered pairs is a linear function. And so when we look at a table, we want to start calculating those differences. Remember, our slope says we're going to take the y values, their change, or their increase or decrease, and compare them to the change in the x values. And I can see that there is a constant change in x. It is plus 2 each time. That is our denominator. And I can see our constant change in y is going down by 1. So we could go ahead and graph this quickly. We don't know our y-intercept yet, but if we were to take this back a couple times or a time and a half, we could calculate that easily and quickly. So the answer to check it out number 2 is yes, there's a constant change. Constant change of plus 2 in the x value or the domain, and a constant change of negative 1 in the y values or the range. Another way of looking at functions is by looking at their equation. And the first thing that we want to talk about is not precalculus, but the standard form of a linear function. Now, don't let this scare you. I don't see any numbers. But that's okay, because A, B, and C, A, B, and C are just real numbers. So if I were to exchange those for values, if we were to see an equation that looks something like this, then we would know we had a linear function because it matches the standard form of the equation of a line. This is a linear function in standard form. If you look on page 232 of your book, you can see linear can look anything like this. We might also have an equation where it contains x and y terms, but they might not be on the same side of the equal sign. That's fine. We also might see negative values of y equaling 5x. And if you go back in the video, you'll see that we also might have terms that just look like this, y equals 2. So these are all linear. If we think about what looks linear, we also might want to compare that to what is not linear. And any function ever containing the product of x and y together, any function containing a power, they have cube in the book, but any power other than 1 in the function, this would not be linear. And any time where we see x or y in the denominator of a fraction, these are not linear functions. So I'd like you to read through example 3 and do check it out 3a, b, and c, and come right back here and we will talk about those solutions. And we're back. How exciting. Looking at checking out problems 3a, b, and c. The directions ask, is this a function? Or, excuse me, tell whether each function, they know they are functions already, is linear. If so, graph the function. Well, let's look at part A, and we know if we see x and y to the first power, x and y both, we could put this in standard form. We could subtract 5x from both sides and see that we can put it in standard form. So we're off to the races. I'm going to use a shortcut here. I know that this is my slope and this is my y-intercept. So I'm going to plot those down here to -9, and a slope of 5 is going to do something like that, and my graph is linear. Looking at y equals 12, y is always 12. When x is negative something, y is 12. When x is 0, y is 12. When x is 1, 2, 3, y is 12. So we have that horizontal line, and we recall that is a function. This, however, x as an exponent, is not a function, and we don't have to graph that. Please look at PowerSchool for your problems to do.